Hi again. Welcome to Zero to LLMOps, the free DevOps course. We spent phase 0 building the mental model, files, paths, users, root, sudo. Today we start at phase 1 and we finally make the sense of what actually happens the moment a Linux machine boots. By the end of today, you will be able to explain in your own words everything between pressing the power button and getting a login prompt. And you will start a script that's going to grow with you for the next 6 months. So let's do a recall from phase 0. Quick recall before we go anywhere new. What's the one character that tells you a path is absolute? Forward slash root. What is root allowed to do? Root, the account. What's it allowed to do? It can do anything. It can read, write, delete any files on the system. It can change any files on the system. What is the single command that borrows the root's power? It's sudo. So I meant to give you a preview of what a booting system is, but it would have been an overkill. That's why let's not take this question for now. In short, what I meant to give you a glimpse of was firmware, grub, kernel, initramfs, systemd, and target. It's the booting sequence, and you need to remember it. So, what Linux actually is? Let's start with the distinction people mix up constantly. Kernel versus operating system. System versus distro. The kernel is one program written by Linus Torvalds starting in 1991, and its whole job is talking to hardware and managing processes, memory, and files. That's it. A distro, Fedora, RHEL, Ubuntu, takes that kernel and bundles it with GNU userland tools, a package manager, and same defaults. So you get something you can actually install and use. We are using CentOS in this course specifically because it's the enterprise standard and it is based on RHEL, Red Hat Enterprise Linux. The RHCSA and RHCE certification paths run through RHEL. It uses the DNF RPM package family and it ships SA Linux by default, which we go deep in week 3. Picture it as a layer hardware at the bottom, then the kernel, which itself separates kernel space from user space, a privilege boundary, then the shell, then your application on top. Let's look at what's actually running under your hood right now. So uname -a gives us which kernel version we are on. So cat etc release gives us the pretty name, CentOS stream 9. ID like RHEL Fedora, ID CentOS version 9, name CentOS stream. Now let's check hostnamectl. Here all the details of our machine are listed here. The static host name is DevOps lab, icon name computer VM because this is a virtual machine. Chassis is VM, machine ID and boot ID. Virtualization used is KVM. Operating system is CentOS Stream 9. Architecture is x86-64 and the kernel is Linux 5.14.0, 721.e19.x8664. Hardware model standard PC Q35 and the firmware which we are running on is based off of Debian Ubuntu. The virtual money machine is hosted on it. So let's break it down. Uname-a gives you the kernel version. ETCOS release tells you the distro and version. Hostnamectl summarizes both, plus the machine's identity in one place. Your new go-to command for what am I actually running. Now, the boot process, stage by stage, 5 stages like a real rally race, each one handing off to the next one. Stage 1 is firmware. This is the very first code that runs, and it lives on a chip on the motherboard, not on your disk. Older machines used to call it BIOS, like it was a separate BIOS chip working with an MBR partition table. Modern machine use UEFI, working with GPT and supporting secure boot. Either way, the job is identical. Power on self-test, wake up the hardware, then hand off to a bootloader. Stage 2 is grub, the grand unified bootloader. It reads its configuration from boot grub to grub.cfg. Shows you that menu where you pick a kernel. So whenever you work in a lab environment, you have all seen that black screen with the list and then loads the chosen kernel image plus something called initramfs into memory. That's grub's entire job. Find the kernel, load it, get out of the way. Stage 3 is the one that confuses people. So say with me, there is a chicken and egg problem at boot. The kernel needs to mount your real root file system, your actual disk, but that disk might sit on LVM or RAID, needing special driver modules. And where do those drivers live? On the disk. The kernel can't mount yet. That's the cache 22. The fix is initramfs, a temporary root file system loaded straight into the RAM. It carries just enough drivers to reach the real disk. So the kernel boots, uses initramfs as a temporary home, loads whatever LVM or RAID modules it needs from it, mounts the real root file system, and then throws the initramfs away. It's a bridge. You cross it once, then you don't need it anymore. Stage 4 and 5 are where the machine takes itself first real breath. In stage 4, the kernel finishes initializing hardware and drivers using initramfs, then does the root swap, drops initramfs, mounts the real permanent root file system, the same slash you have been living in all of the phase 0. In stage 5, it executes the very first user space program on every modern RHEL or Fedora system. That program is systemd and it always gets process ID 1, PID 1. PID 1 is special. It is the very parent of everything else on the system. Every process you will ever run is a child or a grandchild of PID1. It replaced the old sysv init, and one big reason is parallel execution. Old init started services one at a time in a line. Systemd starts independent ones simultaneously, so boot is faster. Let's prove that PID1 is really systemd, not just a claim on a slide. ps-p1-o PID, com. So it gives us the PID and the command, and the PID process ID is 1 and the command is systemd. It's the real machine telling us, it's not me that is telling you that. Now, as ops engineers, we care about two things. How long did boot take and what slowed it down? Systemd gives us three tools for exactly that thing. Systemd analyze alone reports total boot time. Systemd analyze space blame ranks every unit by how long it took to start. This is the command you run first when a server boots slowly. And systemd analyze critical chain shows the actual dependency chain that delayed things, not just the slowest unit in isolation. And it tells us what it was waiting on. Let's run all three. Systemd analyze. So it shows us that our startup finished in 1.85 seconds for kernel, 3.068 seconds for init RD or initramfs, 7.298 seconds for user spaces. The whole thing took 12.226 seconds. Multi-user targets reached after 4.682 seconds in user spaces. Now we are running systemd analyze blame, and here we can see which was the slowest one to load. DNF make cache services. And here in the list you could see how much time the init RD switch root service took, how much cloud KDUM service, cloud init service, chronyd service, all the services that are required to boot your operating system took. Now let's run the systemd analyze critical chain. It shows us the boot times with relation here. So to summarize, blame tells us which your unit is slowest on the machine and is the first suspect anytime boot time feels sluggish. And the critical chain shows you the actual dependency path that made it take as long as it did. Systemd manages everything as a unit, and units come in types. Service is a background program like web server. Target is a group of units that together define a system state. In old systems, we used to call it run levels. If you have heard of that term, you would know. There are also timer units, socket units, mount units. Every one of them follow the same predictable life cycle. One mental model for the entire machine. Two targets matter immediately. Multi-user target, fully networked, text only, no graphical desktop, what almost every real server runs, and graphical target, which sits on top of multi-user and adds a desktop environment. Let's see what target this machine actually boots into and what units exist. We have covered this in day zero, phase zero, like the phase that are foundational, but the people who are little bit advanced and want to summarize for them, we are going to again see those. So systemctl list units hyphen type target, basic system, cloud config target, cloud config availability, NSS user lookup targets, user and group name lookup, NFS client target, NFS client services, network target, network. So I just called out few of the sysinit target, system initialization target, timer unit. I called out some of the important targets. And this is the one we ran earlier. Systemctl get default multi-user target. We have seen this in foundational day zero courses as well. Whatever printed there is the default state that this machine wakes up into every time at the boot. This is worth memorizing because beginners mix it up constantly. There are two separate questions you can ask about any service. First, is it set to start automatically at boot? That's the loaded state, the boot time setting, and you control it with enable and disable. Enable means start this every boot from now on, and it's persistent. It survives reboot. Second question, is it running right now? This instant. That's the active state, the current state, live state, and you can control it with start, stop, and restart, which takes effect immediately. But don't buy themselves survive at reboot. So enabled but not currently started and started but not enabled are both real command situations. Enable is about the future. Start is about right now. The single command that shows you both at once is systemctl status. Let's see a demo of a status for a service. So we see that the service is enabled and it is running right now. This is the main PID of that service, 833. It's the last line in the inline thing. Journal D and journal CTL. Every system needs logs, the record of what happened, especially when something breaks at 2 a.m. System D logging system is journal D, and it's genuinely different from old flat text syslog in three ways. It's native. It captures the kernel, initramfs, and every service output all in one place. It's structured binary, not plain text. So it's fast to query and harder to silently tamper with. And it gives you one unified timeline across the whole system. The tool to read it is journalctl and a handful of flags you will use every single day. Hyphen B is for this boot only. Hyphen U plus a unit name, one service and its log. Hyphen P ERR filter for errors only. Hyphen F follow live. The modern tail hyphen F your ops heartbeat and hyphen since filter by time. Let's use a few together. So, since our last boot, how many lines have been printed in journal dlog? That thing we are seeing here. 1583 lines have been printed. This second command shows that this boot's error. If any empty output here, it's a good news. Now to the terminal properly. Let's go over the labs. Take a screenshot of this. We'll go to the terminal properly for the full lab. You repeat and extend everything we just covered. Confirm your kernel and distro. Run all three. So let's do it. Systemd analyze. So this lists units by target and by service. Now using systemd, let's safely try to stop and restart a non-critical service like chronyd. So you saw that we had to authenticate. The active state is dead here, inactive, and it's the time when we stopped it 9 seconds ago. Now let's start the service. See the status. It's active. It was started 1 second ago, and this is the time since it started. Now let's do a clean restart on it. And to come out of this, you need to press Q, quit. Let's check the status. Again, we had restarted. So it's in running state from 2 seconds ago. So now let's look at few of the journalctl commands. Look at your number of lines from the last boot yourself on your machines. Now let's see for errors. So we had one error regarding DNF make cache from the. Now let's see if we can check any log from the previous boot. So we are running a VM. That's the reason it doesn't allow us to see the previous boot logs. I will check it if my Ubuntu machine has it. So here we are able to see the logs from the last boot. It had 4909 logs, and for the current boot, it has 4848 logs. Let's go into the lab environment again and let's see journal. We will follow for some time using journalctl -f, the tail version of our log. Let's try to SSH into this machine from another terminal, and we see a log here that someone tried to, like, someone is able to SSH in our machine using the SSH key. I am exiting that machine, and that thing is also logged here. To break out of it, you need to press Ctrl and C. Now the last piece, and this one matters beyond today. We are starting a script that's going to grow every single phase for the next 6 months. Right now, it's just proves you can pull together everything from today into one report. So let's create a folder in OPT called as Fresher Project. Give it an ownership of your own, and as we are doing it in OPT and we are using chown command, we need to give the password for sudo. Now let's create a file for our project. So what we have done here is between this and using the cat command and the redirection, we are creating a bootloader.sh file with all this content. Screenshot this so that you are able to create it on your own. Now let's make it executable using chmod plus x slash opt fresher project bootloader.sh. Apologies for the typo here. Chmod plus x opt bootloader.sh. We have made it executable. Now let's run it. To run it, what we do? We simply paste the line. And here it is, the bootloader report. All the commands that we learned and that we put in the file, giving this output. It has everything: hostnamectl, kernel version, total boot time, the slowest units, and any reset errors. If it all makes sense to you, you have just written the first version of a script. You will keep extending it across in the course itself. Now let's do a recap. Linux is a kernel plus distro, led from hardware up through kernel space, user space, shell, and apps. Boot is a 5-stage relay: firmware, grub2, initramfs, kernel init, then pid1 exec, which on every modern system is systemd. Systemd runs everything as units, grouped into targets like multi-server, multi-user versus graphical, controlled with systemctl. Remember, enabled and disabled are about boot time. Start and stop are about right now. And journald plus journalctl gives you one structured queryable timeline of everything that happened. Homework. Run the bootlogger.sh again tomorrow morning after a reboot. If you can and compare the slowest units list. Did anything change? Three questions before you close. Put them in the order kernel init, grub, firmware, initramfs, pid1 exec. Another question is what's the difference between a service being enabled and being active? And what does journalctl minus b minus 1 or hyphen b hyphen 1 shows you that the plain journalctl hyphen b doesn't. Tomorrow's day 2 core CLI tools, the file system hierarchy, and IO redirection, the daily driver skills every other day builds on. Closing this session now. Thank you.